Okay, now today's lectures, actually what happened last time when I recorded the lecture, unfortunately the sound was not recorded, picture was recorded, and what we studied that day was the probability current. I derived that relation on the whiteboard and you have notes. Now you can see that each and every step in that derivation is done very clearly. Now if you have any problem, you can contact me on WhatsApp. And beside that, we did one theorem as well, that the eigenvalue of Hermitian operator are real, and that I also derive it there. Now if you have some problem, consult the book or you can contact me. Now today we are going further. Now what I have written here up there, that is the expression of the probability current which was derived last time, and this is equal to that. This is because this portion is, if you take conjugate of this, this will become psi and this will become psi star, and hence this is complex conjugate of this. And so if you have a complex number z and its complex conjugate is z star, then if it is x plus iy, then it is x minus iy. If you subtract the two, that is z minus z star, you will have x plus iy minus x plus iy. This cancels and that is equal to 2iy. So you can say that. What is y? Y is the imaginary part of z, and you can say that z minus z naught is equal to 2 times imaginary part of z. Now I have used this thing here because this is complex conjugate of that, and therefore you can write it 2 times imaginary part of this, 2 to cancel, and I will disappear because we are talking about the imaginary part, and hence this expression is simplified and can be written in the form of equation 1. Now today we are going to see the use of this equation, probability current equation, and that is, I have taken the potential step problem. You have studied that problem in detail in your BS or third semester or MSc first year. So here is a potential step. You see that this is x-axis, energy or potential is given in that direction, and you see there is no potential at all, there is zero potential here, but as you reach to x is equal to 0, potential suddenly increased to V naught, which is a constant value. It is extended towards infinity. Then the height of the potential step is V naught. Now a particle of mass m and energy E, we don't know energy is greater than V naught or less than V naught, it could be any. It is moving from this side and it incidents on the potential step. Now remember one thing, that if E is greater than V naught, then all the particles will cross the step and they will be going in that direction. However, if E is less than V naught, then classically there is no probability there is no probability of transmission and everything will be reflected. So reflection will be 100%, and if E is greater than V naught, the transmission will be 100% classically. However, if you come to quantum mechanics, we replace particle by wave. So psi 1 represents the wave function of the particle in region 1. Now this portion, psi 1 says that a wave e raised to I k naught x with amplitude A is moving in that direction with plus sign here, and then this much is amplitude is this, is reflected back. Okay, so this portion represents e raised to minus I k naught x in the negative x direction. Then the second solution is, because if you write Schrodinger equation, the Schrodinger equation in the two regions are second order differential equation, it should have two solutions. So the second solution is c e raised to I k x plus d e raised to minus I k x, because now you are talking about this region, and here your Schrodinger equation gives k is equal to that, this being the wave number. K naught is the wave number of the wave here, k is the wave number in that region. So what happens? This portion of the wave is transmitted into that region, and this represents a wave coming from that direction. Mathematically, that is the correct solution, but physically not a correct solution, because no wave is coming, no particles are coming from that direction. The particles are coming only from that direction, and therefore we ignore that. We consider d to be equal to 0, so that no wave is going from that direction. Okay, so that is not there. Beside, in order to simplify that, we say A is 1. A1 means that unit amount of particles, they are going with wave number k naught in positive x direction. Then out of 1, B amount is coming back in the same region in negative x direction. And then this C is R, C is R, B is R and C is T. T means that much is transmitted into that region. So let me repeat it again. One amount of wave is going in that direction, R amount is coming back, that is reflected, and T amount is transmitted into that region. And that is the wave number. This is also the wave number. This wave number is greater than this, because this quantity E is greater than this one, because something is subtracted from here. Now, when wave number is greater, what about the wave? Okay, you see wave number is 1 over lambda, and lambda will be equal to 1 over k. Okay, so when wave number increases, lambda decreases. So what happens, this wave number is larger and lambda will be smaller. So de Broglie wavelength associated with the particle is smaller here and it is larger there. So if you write it, wave like this is going there with smaller wavelength, and here wavelength is larger like that one. Now the question is, if I ask you, find the probability current of the incident particle. Find the probability current of the incident particle. Now remember, incident particle wave function is that, with amplitude A, so that is your psi. So what you will do, you will use that. You will say, well, J or S is equal to h bar over 2m, imaginary part of psi star. Complex conjugate of this is minus I k naught x into delta over delta x, because we are working in one dimension, not in three dimension. Delta over delta x of psi, which is e raised to I k naught x. And this will give you h bar over 2m, imaginary part of e raised to minus I k naught x into differential of this is e raised to I k naught x into I k naught. Derivative of this. This will give you 1, because this both are with opposite sign, and you get h bar over 2m, imaginary part of I k naught. Now, this is the only part which you have. Remove I and you will say h bar k naught over 2m. H bar k naught over 2m, that is the current of incident particle. This is the current of incident particle h bar k naught over m. H bar k naught over m. Now, you know, this de Broglie hypothesis says momentum is h bar k. So that is p naught over 2m. P naught is mass of the particle into speed, and that is 2m. Okay? And this mm cancel. So that is it means that this is moving with probability current which is half of the velocity of the particle in that side. ठीक है, ये लिखने की ज़रूरत नहीं है, मैंने ऐसे आपको साथ बता दिया कि अगर कोई पूछे तो आप इसको ऐसे भी कर सकते हो. Okay, now the next thing. Now my question is, calculate the probability current of the reflected particle. आपने अब रिफ्लेक्टेड की करनी है, ये तो आपने क्या कर दिया है, this is of the incident particle. Now the probability of the reflected particle will be the probability current. Let's say this is J1 या J incident and J reflected. Okay, that will be equal to h bar over, sorry, ये 2 तो नहीं था इसमें, इसमें ये 2 तो कैंसिल हो जाना चाहिए, ये 2 कैंसिल कर दें, आई एम सॉरी, ये 2 नहीं होगा. ओके, तो फिर ये V नॉट इसका आंसर आएगा. ओके, आई मेड ए मिस्टेक, प्लीज करेक्ट इट, because this 2 will appear because this is 2 times, okay, imaginary part of that, so this is 2 cancels, so no problem. Now this is equal to h bar over m, imaginary part of psi star. Psi star of what? Of reflected. So this is r e raised per I k naught x delta over delta x, or e raised per minus I k naught x. Now if you simplify this, this is imaginary part of r square, right? E raised per I k naught x, derivative of this minus I k naught x into minus I k naught. ठीक हो गया. अब now what to do? This cancels with that one, and that is equal to h bar over m minus I k naught, and this is further equal to h bar over m minus k naught, because imaginary part means I will disappear. Very strange. Look at that. This is equal to that. Okay, लेकिन उसके साथ r square भी है. There is r square with that. So it means that k wave with probability current, this is moving in that direction. Out of that wave, this much is coming back. ठीक है? Okay. Then what is the difference between the two? J in plus JR reflected. If you subtract this from that, because this is J reflected, if you subtract this from that, you will be getting, what you will be getting? H bar K naught over M into 1 minus r square. H minus 1 minus r square. Now, then I am going to ask, what is the probability current of transmission? Okay, so you will be using that. Okay, and then I don't need to calculate it, because from symmetry I can calculate it. देखिए मैंने जैसे ये calculate किया, I can say that J transmitted is equal to, देखिए ये माइनस तो इस वजह से आया. Now this thing and this thing are the same, and hence I'll be getting H bar K naught over M, लेकिन इसके साथ 1 था, T तो इधर T स्क्वायर आ गया है. It is. This is the probability current of transmitted particle which are going in that direction, Now, if you study, which I have given you as an assignment to read it, this potential step problem, then you can see there that r square plus t square is equal to 1. That is square of this r, square of this t, and this r square is known as r dash transmission coefficient. Reflected coefficient. And this t square is the transmission coefficient. Now remember, some books, they don't write r square, they write r plus t is equal to 1. Now r mean r square because I have used different symbols. I have taken a is equal to 1, b is equal to r. So if you don't do that, okay, you leave a is equal to a, b is equal to b, c is equal to c and eliminate that, then of course you will be having some a square there and b square somewhere and c square somewhere, and then from there you can say कि भाई ये चीज़ r के बराबर है और ये चीज़ t के बराबर है. So this depends upon the book, which book you are following. Okay, तो बात ये है, it is the physical outcome of these relation के reflection coefficient plus transmission coefficient, and it should be equal to 1. मतलब ये है, just look कि if 10,000 particles are going in that direction, out of which, let's say, 7,000 particles are reflected back, 3,000 are going in that direction. So 7,000 plus 3,000 are 10,000. This is the law of conservation of particles. Okay, how many particles are going in that direction? You see on the other side कि भाई only out of 10,000, let's say 8,000 are there. बाकी किधर चले गए? Where are the other 2,000? तो आप कहेंगे कि ठीक है, प्रॉब्लम तो नहीं है. Okay, तो where are the other 2,000? तो आप कहेंगे definitely they have gone back. They haven't been transmitted, but they were reflected. Okay, now this is the beauty of quantum mechanics कि classically, अब देखो, somebody, if this wall is, you know, it doesn't have any door or window and there is no roof there and I am trapped here, or somebody says कि can you go to the other side? I am coming, you know, walking from there, and says कि can you go to the other side, then classically there is no chance for me to go there. Lekin quantum mechanically, because there is a wave function transmitted wave function which is